Lecture 7.5, the mathematics of two-slit interference. The geometry of a two-slit experiment looks like this. So let's set this up. So I'm going to have my slits. And then I'm going to have my screen. And of course, I have my central line. And in fact, I think I'm going to copy this for later on. So I'm going to draw a dashed line here. And one of the things that we've already said here is that this guy right here is our slit separation, which we called little d. We call this guy right here our screen distance, which is big D. And so I'm going to copy this for future purposes. So now what we're going to do is that we're going to pick one fringe location. I don't know whether it's a bright or a dark. And then what we're seeing here is that we have two rays or two waves. One wave is coming from, let's say, slit number one. Okay, so this is slit number one or ray number one. And then I'm going to have a second one that's going to come from slit number two. And what we're going to find here is that there are two measurements that one could make at this point P. One, we can have a screen location, which is y of m being measured from the central line. And then we could also have an angle that we measure. And this angle right here is the angular location, theta of m. Now it turns out that those are the two important parameters. So let's go start to look at this thing. So when I look at this, in fact, I think I'm going to copy this here because I'm going to need both of these. What I want to do here is that I want to set this up. So I need to, the first thing that I got to say here is that to mathematically derive the equations for the screen location of a fringe we need equations for y of m and theta of m. This gives us two important triangles. Let's identify these triangles here. So I'm gonna modify this thing that we just did. First thing I'm gonna do is I'm gonna get rid of this guy here, and I'm gonna try to, like, I already know that this screen just here, let's just start drawing. The first thing that I want to do here is that I know that this is little d, and maybe I should have drawn this a little bit bigger here, but look what I'm gonna do. These two lines, so let me draw a perpendicular line between the red and the green line. So this guy right here is a perpendicular line. Now, I know that the green is number 2, and I know that the red is number 1. The first thing that we want to do here is that this forms our first triangle right here. Okay. Our second triangle is going to be this triangle that defines that angle theta m. So what I'm going to do here is that I'm going to start labeling these triangles. So the first thing is that I'm going to call, I'm going to move this D here out, but we know that the separation is D. So I'm going to label this point right here 1. I'm going to label this point over here 2. And then I'm going to label this point 3 right there. So you could see that the blue triangle, right? So there's 2 triangles. So the blue triangle is the triangle of 1, 2, and 3. And then I'm going to label the yellow triangle, which I'm going to call this A, B, and P. So then the yellow triangle is, and I'm going to use the angle symbol for A, B, P. And I do know that the path difference is R2 equal to R1 plus delta R. So what you're seeing here is that if I drop that blue perpendicular, that means that these two guys have to have the equivalent distance, the equivalent length. And so this little extra piece is now called delta R. So now, here we go. And this is where it gets a little bit tricky by what happens, because now, look what I'm going to do. There's theta m, right? Here's theta m. And I'm going to say that this angle of the yellow triangle is going to be similar, it's going to be equal to this angle theta m right there. And I'll explain why I'm going to say that. So the first thing I'm going to do here is that I want to look at the triangle. Excuse me. I want to look at the blue triangle. Which will then be triangle 1, 2, 3. So if I look at this thing, I'm going to rotate that triangle, and it's going to look like this here. If I rotate it, and so here's my triangle. And then I'm going to label my points as 1, 2, 3. So you could see that the distance, by the way, 3 is perpendicular to 1, like this, and 2. So this distance here is delta R. This distance is little d, the screen separation, and this is the angle that I've been calling theta. So now if I solve for the path difference, delta R, then I see that delta R over little d, because it's the opposite angle or the opposite side, is then going to give me sine of theta. So then delta R is then going to be d sine theta. So it turns out that this becomes an important relationship for two-slit interference, and you'll see in a minute why. So that's what solves here for delta R. Now remember, delta Y is associated with delta R. Now the next triangle, I'm going to look at the yellow triangle. And this is A, B, and big P. Now this one, the way it's set up is it looks something like this. Now if I label these points exactly the way they look like, this is A, B, which is at perpendicular angle right now, and that's my point P. This is my angle theta, and this is my screen distance, capital D, from there to there. So now I know that this distance is my screen distance from the central line. So now I can solve for the screen location of the fringe. So in this case, this guy here is, it's going to be the tangent, which will be y of m over big D. That's going to be tan of theta, which then gives me the relationship y of m is equal to d tan theta. So if you go back to the original picture that we had, the two things that I drew here was y of m and theta of m. We needed these two equations, and you see the blue and the yellow triangle gave me these two equations. Now, there's something slippery that I did not, immediately state what happened here. The only way that theta m and theta, the angle of the blue triangle and the angle of the yellow triangle are the same is if there's an approximation, because they should not be the same. Okay, so the only way the blue triangle angle and the yellow triangle, I could have said this better, angle are the same, because remember, they are not the same, is if little d is much, much smaller than the screen separation. only in this situation can the angle of 1, 2, 3 be approximated to be the angle of ABP. That's the only possible way. So, and it turns out that for interference, that's usually the case. So, there are two possibilities. And I'll call this case number 1. In case number 1, we have no small angle approximation. So if this is the case, then the pair of equations must be solved simultaneously. Not simultaneously. So in other words, we have to use this guy and this one to calculate any of the details. So that means here, if you want to play it safe, you solve these two equations for all possible situations. That is, to play it safe, your best bet is to solve these two equations for all possible situations. And in interference, it turns out that the small angle approximation works most of the time. In diffraction, it does not work most of the time, which is going to be later on in this chapter. So just putting it out. Now, there's a second situation. And this is case number 2. Here, this is the small angle approximation. So what happens in a, right? So I guess in defiance of playing it safe, the most common way to solve for the fringe location is the small angle approximation. So here, the reason why the small angle approximation here is because we can use a Taylor expansion. So using a Taylor expansion for sine of theta and tan of theta, shows that the Taylor expansion of sine is really theta minus theta cubed 3 factorial. And I could just keep going on and on and on, but I'll leave it right there. And you could see here is that for a small angle approximation, this term and this term are really, really small. So you can approximate this as theta. On the other hand, if I look at tan of theta, which is of course sine of theta over cosine, this becomes a very similar process where this becomes what? It's going to be sine of theta over cosine of theta. But if I do a Taylor expansion of this, we just saw that the numerator is 1, excuse me, is theta, but cosine is actually 1 plus these other terms. So then I can approximate this to theta as well. In other words, we can equate sine of theta to tan of theta, which is also equal to theta for a small angle approximation. So now that this is going to really change the two interference equations. So the two interference equations can be simplified into one master equation. Not two, but one. But you could see here is that delta R, which is d sine of theta. Now I can approximate this as d theta. And then y of m, which is big D tan of theta, I can approximate that to d theta. So now I could now eliminate it's not the way you spell eliminate. Theta from the equations so that I get y of m is then going to be big D, little d times delta R. And this is an approximation. So a small angle approximation gives us that this is the fringe location on a screen. And that's the master equation right there. So if I now apply this to interference, okay, so now let's apply the path difference for constructive. And what do I mean by constructive? That means that delta R is going to be MC lambda, and destructive, which means here that delta R is then going to be MD plus 1/2 times lambda. To the fringe location. And it reads something like this. So I'm going to have y of m And this is going to be d little d times delta r. And this will then equal, it could be MC d lambda little d, or it could be md plus 1/2 of d lambda d. And this will be bright fringes. This will be dark fringes, where MC and MD have the same values. Now, I want to say one thing before I move on, is that, remember, this guy is measured from the central line. Okay, it should be delta y of m, but that's not what's common. So now what I want to do here is that I want to start to interpret these fringe locations here. Okay, so now we're going to start our interpretation of the fringe location equation. So it's clear that the fringe locations depend on 3 parameters, right? It's clear that the fringe location equation only depends on 3 parameters, which are lambda, little d, big D. So for 2 adjacent fringes, I can then see that delta y of m is then going to be MC plus 1. Let's say I just focus on the bright fringes, but it's going to be the same for the dark. This will be d lambda over little d minus MC d lambda over little d, and this becomes d lambda d. So this equation also applies to dark fringes too. So I'm going to use this equation right here. So my focus now is that this equation, what it tells me here, is it tells me about the separation of the fringe distances between adjacent fringes. So what I'm going to do here is that I'm going to look at FET, not FET, FENT, interference applet. This is not my preferred applet. And the main reason why, because it doesn't have the screen distance. I need all 3 parameters to really show that. But this is not going to allow me to do this. So what I'm going to do here is that I'm going to use it to talk about the wavelength, to talk about the slit separation, but I'm going to use images of another applet that's now deceased. So the images will be different, but the ideas are going to be exactly the same. So in other words, I'm going to use the Fent applet to look at changes in lambda and little d and see the effect on the fringe separation. For big D dependence, I cannot use the applet. So I'm going to use images from a different applet. So here I go. So the first thing that I'm going to do is that I'm going to come in and I'm going to start to look at what happens if we start to look at fringe separation with changes in the wavelength. Okay, so here we go. So I'm going to look at fringe separation. In this case, has to be directly proportional to the wavelength. In other words, if you look at the fringe separations, they're directly proportional to the wavelength. So that's what we really want to look at right there. So if I start to ask the question, I'm going to go something like this. What happens to delta y of m as lambda is changed? That's what I'm really asking. Well, clearly, if you looked at it's directly proportional, we can clearly see that if we have longer waves, that has to imply that we have larger. How do I do this? Let me move this here a little bit over. So if I have longer waves, then the wavelength is going to be longer. Therefore, I should have larger fringe separations. In other words, this guy should grow in size. On the other hand, if I have shorter waves, then that means here I'm going to get smaller waves. And as a consequence, I should have smaller fringe separations. So then this guy should be, they should get tighter. So let's go look at the applet. So the applet says, if I go and I share it, so here, this has a really, so I'm going to fix D here. So how about if I do this? Let's see, what value is that? How about if I look at 2000 nanometers? Okay, there's my, that's my, so you could see there, I have light that's coming in. It goes through two slits, even though it shows one, but it is two slits. And then what it does here is that this is the pattern that you're actually seeing. Now look what happens here. So this is a short wave, and look at the fringe separation. Now I'm going to increase the waves, and you can see that the fringe separation has spread out. And if I make it even longer, you see that they spread out even more so. So now, if I go back to my applet, remember I said I'm going to use a different applet, images that is, and it's going to look something like this. So what I have here is I have this guy. This is the deceased applet. And then here's the next image. So now, why did I pick this applet? For starters here, look what's fixed here. This distance is, this is big D. And you could see that big D here, this distance is fixed at 0.8. This is big D, it's fixed at 0.8. Now, another thing that you should pay attention to is that this is little d, and you can see here that little d here is also fixed. So the only thing that I'm changing here is the wavelength. And look what I'm seeing here. This is lambda, and you could see here that that's 700 nanometers. This is lambda over here, and you could see that this is 400. Now, what I like about that is that look what it does here. What it does here is that I'm going to look at the separation of these fringes here. And this is delta y of m. So if you look at this thing, you could see here that maybe what I should do here is that this guy is wider compared to this guy here, which is smaller. So I'm seeing the difference between the fringes, and then I'm looking at the intensity profile, and it looks like that. So now, here I go. So what you're seeing here is that you're seeing here. So if I look at that, I'm just going to look at what I have here. I see that D and big D are held fixed. They're constant. So in this case, I have a wavelength of 700 nanometers, which is red light. And this actually is blue light, not green. And then here, you could see here is that this wavelength is 400 nanometers, and you can clearly see that it's shorter. So here's what we said already, right? Longer waves increase in delta y of m. So in other words, in this case, I get a bigger fringe separation because the wavelength is longer while holding d and little d fixed. On this other situation, we have shorter waves, which then tells me that there's a decrease in delta y of m. So in this situation, what you're seeing here is that I have a smaller separation because I have a smaller wave compared to the red one. Okay, so now let's go look at the screens, the slit separation. So now two here, I'm now going to look at the fringe separation. And this is proportional to 1 over the slit separation. Again, when I look at this, this is really telling me that little d is inversely proportional to, the adjacent fringe separations is proportional to 1 over d. So then here I go. I'm going to start the same thing. Question: how do the fringe separation behave as little d changes? Well, if it's inversely proportional, we can see here that if I have a smaller slit separation, in other words, my little d is tiny, then that tells me here that I should have a larger fringe separation. In other words, this guy should be big because it's proportional to 1 over little d. On the other hand, if I have a larger slit separation, let's call that big D, then I should have a smaller fringe separation. That means, in other words, this guy should be small because this guy is large. You know, I realized I didn't really physically explain part 1. I'll come back and look at that. Let's keep going here. So now let's go back to the applet to look at what we're talking about. So now what you're seeing here is that I'm going to fix my light. Let's fix this to be about, oh yeah, how about 680 looks perfect. So now look at my fringe separation. Okay, look at that. This is at 2000. What's going to happen if I make the slit separation even smaller? So if I go from 2000 to 1000, I should see the fringes get farther apart. And they do. If I increase it, I get closer fringe separations. So it's exactly what we're expecting to see here. So now, if I come back to my screen here, I'm going to copy those same applets, the images of that applet that I really like, and then show you what do I mean here. So what am I seeing here? So the first thing that you want to see is that you can clearly see here that these guys are definitely much bigger than these guys. So this guy from here to here, and these guys are definitely much larger. So what's fixed here? So what's fixed here is that you could see that my wavelength in each of these situations is fixed at 700. Now, the other thing that should be fixed is look at the big D. Big D is also fixed. So the only thing that I'm changing is the slit separation. And so in this situation, this guy is going to be little d right here. And then this guy over here is going to be little d2. But note that this is 7 millimeters. This guy's 1 millimeter. So once again, playing the same game as we did before, we see that lambda and d are held constant. So now, if I have a smaller slit separation, in other words, I have a tiny little d, then that tells me I'm going to have a large delta y. So equation-wise, it's exactly what we would have expected. I'm going to see here is that this guy is big Y of m, and the reason why this works here is because this guy in the denominator is tiny while keeping lambda and d fixed. On the other hand, by the way, I should have probably written that this guy here, that this is 1.0 millimeters. That's what I mean by a little tiny one. And then this guy here tells me that little d is 7 millimeters. So you could see that it's 7 times larger. So we then find that we have a larger slit separation. So in other words, this is big D. As a consequence, I'm going to get a smaller fringe separation. So if I look at this equation here, it tells me that this is a small one because D in the denominator is large. And so now I can't show you the applet for screen distance. So now we're going to look at the fringe separation. Proportional to screen distance. And that implies that delta y of m is directly proportional to d. So then we ask the same question. What happens to the fringe separation as the screen distance changes? Well, if I have a smaller screen distance, we can see that it's proportional, then that distance is going to be a little d here. That tells me then that I'm going to have smaller fringe separations. Delta y of m. On the other hand, if I have a larger screen distance, let's call this big D, then I'm going to get large screen separations. Again, because it's directly proportional. So now, since I can't show you in the applet, I do want to show you the images. And again, this deceased applet, I was very disappointed that they stopped supporting it. Mostly because it was done with Flash. So what's fixed here? What's fixed here is that you can see here that the, in this case, look at the little d here. And then this guy is the wavelength here, and you could, oops, that's not the wavelength. This is the wavelength here, and you could see this is 700, and this is 3.5. And you could see here is that this is little d, and this is fixed, and this is lambda, and this is fixed. So we see here is that lambda and little d are constant. and do not change. What does change is going to be the screen distance. So if I look at the screen distance, here's what I'm seeing here. This guy is little d here, and so little d here in this case is 0.3 meters. On the other hand, this d over here is going to be larger because it's 0.8 meters. So look at the fringe separation. In this case here, you could see that the fringes are just little tiny y of m's. Here, you're seeing that the fringe separations are bigger, not much bigger, but they're definitely bigger. And so then we could start looking at our process here. So if I have a smaller d, then that means I'm going to have a smaller fringe separation delta y of m. And that's because delta y of m is directly proportional to lambda little d big D, like this. In this situation, we're going to have a larger D. And if I have a larger D, then this tells me here is that I have a larger separation delta y of m. And the reason, again, is because this guy is directly proportional to the screen separation. Now, physically, let's go back and look at these. I didn't say anything about this, so just as a way of finishing this off here. So if the fringe separation depends on the wavelength, and I change the wavelength, what happens here? One way to think about this is that physically, if the waves are longer, there are less locations where they can or will produce constructive interference. And because there's less locations, then the fringe separations have to increase. If I have smaller wavelengths, then there are more locations where the fringes can interfere and produce constructive or destructive. So then the fringe separations have to decrease. In a very analogous way, when we go to the slit separation, what we're seeing here is that as the slits get closer together, there are less spots for the waves to overlap. And because there's less spots, the fringes have to get farther apart. If the screen separation is larger, then there are more spots to overlap, and therefore the fringe separations have to get closer together. And then finally, when we go to the screen distance, this is just about distance. If I have a close distance, then the waves can't spread out as much. But if I have a farther distance, they spread out more. So therefore, if I have a farther distance, the fringes have to separate.